Today's lesson is on molecular formulas, carbon-hydrogen combustion analyzers, and percent of a hydrate.
Okay, so we have here 7.3. This we're continuing from last class, and last class we were looking at empirical formulas, and empirical formulas are simplified versions of the simplified versions of the molecular formula. So let's look at a table here. Okay, so many compounds can have the same empirical formula. So they're just simplified versions of them, right? So if you look at all of these, right here, we've got 6 different examples of 6 different compounds who all have the exact same empirical formula. That empirical formula happens to be CH2O. We've got things like glucose, we've got ribose, we've got erythrose, lactic acid, acetic acid, and formaldehyde. Okay, so if and here's a very important step: if I can find the molar mass of just the empirical, as I have here. Okay, so I've got this empirical. Let me change this. Make it red. Hold a bit. So there's the molar mass of, and let me put units, actually grams per mole. So there's the molar mass of formaldehyde, which happens to be the empirical formula of all of these. If I find the molar mass, if I find the coefficient that allows me to go from this empirical to this, okay, to the acetic acid, this acetic acid is a multiple, we would multiply by 2. This one here, we would multiply by 3. This one, we'd multiply by 4. This one, we'd multiply by 5. And this one, we'd multiply by 6. Because this one here with 6, this is has been multiplied by 6. Okay, so all we need to do is find the molar mass of the empirical and multiply by whatever that value is. So if we want to find the molar mass of glucose, well, we could take the empirical formula of glucose and multiply by 6, because it is the glucose molecule is a multiple of 6 from its empirical formula. Okay, so with this lesson here, not much to it. It's a very short lesson, and that's pretty much it. Okay, what we did in 7.2 is the toughest part, our ability to get to this. But in order for us to go from an empirical formula to the molecular, we must know what that possible molecular formula is. And that's where we're going to see these sample problems. Okay, so let's look at the sample problem here. And this without looking at, of course, that table that we just saw, because all the answers will be on that table. But here we go, 2 sample problems. The empirical formula of ribose is CH2O. In a separate experiment using a mass spectrometer, the molar mass of ribose was determined to be 150.05 grams per mole. What is the molecular formula of ribose? So here we have that equation. So what we want to do is, whenever we have an empirical, always find the molar mass of that empirical. Okay, and that's what we have here. Okay, that's what we have right here. Okay, 30.03 grams per mole. That's the molar mass of the empirical, and it's not in the question. Okay, it's not in the question. The only value given in the question is the molar mass of what our molecular formula is. But right now, if this happens to match the molar mass of this, then we've then they're the same. But in this case, they're not, because we found here the molar mass here of the empirical, and up here we've got the molar mass of our molecular formula. So what we do, what we divide is we take the molar mass of the molecular and we divide it by the molar mass of the empirical. Okay, so we take the larger of the two values, we divide them, and we realize that it is 5 times its molar mass. So what we do is we take that 5 and we multiply all the elements in our empirical by 5. Okay, so that C gets multiplied by 5, that H2 gets multiplied by 5, and that O also gets multiplied by 5, which will give us the molecular formula of ribose being C5H10O5. Okay, so that's how simple figuring out the molecular formula is once we know what the empirical is. So the hardest part is getting to this. Okay, that's 7.2. That's last class's lesson. Okay, this lesson carries over what we did, right? Percent yield, percent composition, calculating empirical formulas. Here, we are taking what we did in 7.1 and 7.2, and now we are trying to see how much bigger is the molar mass of our actual molecule in comparison to its empirical formula. And that multiple is what's going to tell me how much, what is that molecular formula going to be based on the molar mass. Let's look at the last sample problem here. A compound has a formula of C6. We put X in this case, H5X and OX. So another way to treat this formula is really C6H5O. Ignore the X's, okay? Ignore the X's. Okay, this is what that means. But that X just implies what are we going to multiply all of these little subscripts by to actually find that molecular formula. So the first step is going to be to find this molar mass. Let's find this molar mass. And that molar mass of C6H5O is right here, 93.11 grams. Okay, 93.11 grams for those who can see it. So what we do, we take the molar mass here of the 186 grams per mole. That's the molar mass of the bigger one. Be aware that you're trying to find actual whole number. Like they're always going to round to the exact whole number, all of these questions. If they don't, you did something wrong along the way. You probably calculated the molar mass incorrectly. But anyhow, so we take the 186 that is given. That's the molar mass that typically should be given to you. You'd be using a mass spectrometer to find that. You're not going to be able to calculate that any other way other than calculating our empirical as we did in 7.2. So we take the 186 grams per mole divided by 93.11 grams per mole, and we realize that it was a value of 2 times that of the empirical. So what we do here at the bottom, okay, we've got we're multiplying each one of these elements by 2 to give us a molecular formula of C12H10O2. Okay. So let's move on to 7.4. Okay, 7.4 can get a little bit tricky, but it's still carrying over the stuff that we have just done. Okay, so 7.4 carbon hydrogen combustion analyzer calculation. Every type of these questions all work the exact same way. So if you see the pattern in all these, you'll understand how they all work. So let's figure out what this is. What is a carbon hydrogen combustion analyzer? First off, okay, so this carbon hydrogen combustion analyzer is an instrument used for analyzing these types of chemicals, carbon, hydrogen. Okay, so what you have is you've got some kind of furnace where you're going to burn in the presence of oxygen. So you're going to burn in the presence of oxygen, And you've got these absorbers. You've got these water absorbers, and you've got these carbon dioxide absorbers. Okay, so what we are collecting is water and carbon dioxide, and using these carbon hydrogen combustion analyzers, we are trying to figure out what is the empirical formula of any hydrocarbon. Okay, any compound containing carbon and hydrogen. Okay, so we use these analyzers. Okay, don't worry about what's in these absorbers. The only thing that I want you to worry about is that these carbon hydrogen combustion analyzers, what they do is they absorb carbon dioxide and water. What material, right? Like one of the absorbers here is magnesium perchlorate. Who cares? Okay. The other one here, sodium hydroxide. Again, I don't really care. The only thing I care about is the fact that we are burning a hydrocarbon, some unknown hydrocarbon, right? And when we burn it, we need oxygen. So we put oxygen in, burn it. We collect water. We collect carbon dioxide, and of course, there's going to be oxygen and a whole bunch of other gases that come out, but we are not absorbing those. Okay, so forensic scientists, food chemists, pharmaceutical engineers, and other types of chemists, they will utilize these kinds of values. So they're going to try to do is try to find the percent composition of these compounds. Okay, so that's it. Okay, what makes these, I guess, tough here are the sample problems. Okay, we're going to go straight to the sample problems because that's really what I'm looking for, aside from the knowledge stuff that I've just shared with you about what are we collecting in these analyzers. Okay, so first sample problem here, it's only one sample problem actually. So we've got a 1 gram sample. So we take that 1 gram of an unknown substance. We don't know what's in it, but all we know is that it's made up of carbon, hydrogen. That's all we know. We've collected a 1 full gram. Sorry, did I say 1,000? I might have said 1,000. 1 gram of it. So we've got that 1 gram, and we're going to burn it in that combustion analyzer. And in the end, when we collect the water and carbon dioxide that these analyzers absorb, they collected 0.6919 grams of water, and they collected 3.38 grams of carbon dioxide. And so what we have here, okay, what we have here is now a greater mass, right? And notice here, we start off with 1 gram, but all of a sudden we ended with so much more. Understand that that's so much more is all the oxygen that's input. So what we want to do is try to pull out how much of this is actually carbon, how much of this is actually hydrogen. Okay, so that's ultimately what we're trying to do. So we're trying to calculate the masses of carbon and hydrogen in this sample. Okay, so let's go straight to the sample problems for part A. Okay, so here is part A. We're trying to calculate the masses. Okay, now in the water sample, what we have, we collected this much water. Okay, we collected 0.6919 grams of water. Of that water, if we find the percentage of this mass that is made up of hydrogen, we could figure out how much of this mass is in fact made up of hydrogen. And to do that, we look up, well, in all of water, we've got a molar mass of 18.02 grams. Of that 18.02 grams, we've got 2.02 grams of that being hydrogen. So if we take these two values and we divide them and multiply it by 100, we get an actual percentage. We don't care about that percentage. We're going to utilize that percentage and multiply that by this mass instead. So we're going to skip finding the percentage, because even if we found the percentage, we'd have to take that percentage and then still multiply it by this value. So why not, instead of multiplying it by 100 to find the percent, multiply it by the mass of the water that we collected in the absorber to find how much hydrogen we in fact have. Okay. Secondly, the mass of carbon sample here, we've got, we're doing the same thing, but in carbon of carbon dioxide. So we've collected 3.338 grams of uh, of carbon in carbon, of carbon dioxide we've collected from our sample. But understand that a lot of that mass is made up of the oxygen that we were burning. Okay, so what we have here is we take, again, we're trying to find the percent composition of carbon in carbon dioxide. So I found the molar mass of carbon. I'm dividing it by the molar mass of carbon dioxide. See, there's only one C in CO2. There's two H's here in H2O. That's why we use two H's, right? So look really closely to the to those values. And again, we could multiply it by 100, but let's skip that times 100 and multiply it by the actual sample. And when we multiply by the actual sample, we get this mass. Okay. And one thing to make note of is once we've found our values, okay, these values here that we just calculated should, and ballpark wise, it's never exact, but it should be close enough to this 1 gram sample that we started with. So what we have here is all this excess mass is made up of oxygen. All this excess mass here of the 3.38 grams is actually, in fact, oxygen that we are burning in it. But in that absorber, we're collecting water and carbon dioxide. It's the hydrogen that we want. It's the carbon that we want from all of these values. Okay, so these are the things. I'd say these are the steps in how to calculate the masses of carbon and hydrogen. Okay, let's look at the second part of the question. This first part of the question, this is this exact same wording. Is the part B of the question says find the empirical formula of that compound. So we found the mass of carbon in part A. We found the mass of hydrogen in part B. So we do the same steps to find these C and the number of moles, right? So we take that value that we found in part A, and we divide them by their respective molar masses. So in this case, this is the mass of carbon, and we divide it by the molar mass of carbon to find the number of moles of carbon. We take the mass that we found of hydrogen in the first part, and we divide it by the molar mass of hydrogen to find the number of moles of hydrogen, and in which case we end up getting these values, this C something and this H of something. Okay, so remember, as we said, one of the steps typically when calculating the empirical, oftentimes one of the empiricals simplifies to 1. So how do we simplify that empirical to 1? We divide all of these values by the lowest of all the values. And the lowest of the values happens to be that of hydrogen. They're very close between the two, so it doesn't really matter, because in this case, you'll notice that they actually simplify to C1H1. Therefore, the empirical formula of this unknown substance is CH. Okay, so there you have how to go about calculating the mass of carbon and hydrogen in a combustion analyzer, and how to go about calculating their empirical. One thing to make note of, and this we're going to go back to the first part of this question, is what if this unknown substance, this 1 gram unknown substance, contains carbon, hydrogen, and oxygen? Let's just say, what would we do to calculate oxygen? Now, to do that, okay, to find this part, this oxygen part, you would not do this method, because remember, when you're burning something, when you're burning a hydrocarbon, you're adding oxygen. So if you do these calculations this way, but with oxygen in, let's say, the O in water here, or the O in CO2, understand that part of that O is actually from what's coming into the system to burn it. So what you would do is to calculate that. You're finding hydrogen this way, you're doing carbon this way. These are the only two you should be doing this way. And then when you add these two values up, you would add them and subtract them from your overall sample. And whatever's left over will be, in this case, would have been oxygen if this example actually had oxygen as an additional mass to find. Okay. There are, I think, some of the sample problems that do have that third value to find. So practice that so you can understand what I'm talking about in this scenario. But otherwise, um, this method is what you're using to find carbon and hydrogen. Maybe nitrogen might be an unknown. Again, same thing. Find that of carbon, find hydrogen, add those two values, subtracted by what the given sample, and whatever's left over is going to be the value of that nitrogen. Let's say if nitrogen happened to be in this scenario here. Okay, so that's 7.4. And the last one for this evening, 7.5. Here we go. Determining the formula of a hydrate. Okay, so let's just recap. What is a hydrate? A hydrate is some kind of an ionic compound that has water molecules incorporated within their crystal structure. Okay, and that's where we use the Greek prefixes and the term hydrate to tell us how many of that value we have. Okay, so here's an example: Epsom salt, magnesium sulfate, and here this well, it's supposed to be a dot, 7H2O. So that's a heptahydrate. So we've got 7 molecules of water weakly bonded around magnesium sulfate. Okay, so let's go straight to the sample problems because all it is really, it's just calculations using specific types of concepts, utilizing percent composition, empirical formula. Okay, that's really what these last two lessons happen to be, and they're pretty much very much sample problem based. Okay, so let's look at the one sample problem that we have here. So we've got a hydrate of barium hydroxide, and we don't know the value of the water. We're trying to find what that number for water of the water is. Is it a monohydrate, dihydrate, trihydrate? What is it? Whatever it'll be, that's what we're going to be eventually calculating. Is used to make barium salts and to prepare certain organic compounds. Understand, sometimes there's a lot of wording in a sample problem just to kind of give you a little bit of the chemistry behind this reduction, and that's what this case happens to be. So what we have here is we've got a 50-gram sample of the whole thing, okay, of whatever this water happens to be. That whole thing is 50 grams, okay? But now 27.2 grams of this, or 27.2 grams of this 50 grams is barium hydroxide, okay? So calculate the percent by mass of water in barium hydroxide, and then eventually part B asks us to find the value for X. So part A should be relatively simple. Okay, part A, we take the full 50 grams, we subtract it by 27.2 grams, okay, and we get a value for how much water happens to be. In this case, it would be 22.8 grams is actually water, right? The remaining of that 50 is water. So if we take that value, we divide it by 50 grams for the entire sample, multiply it by 100, 45.6% of this 50-gram sample is made up of water. That's a lot of water. Okay, it makes up pretty much half of its mass. Okay, so the part B asks to find what is that unknown value, and that's where we end up utilizing what we've done in calculating the empirical. But now we're not trying to find the empirical formula. We're trying to utilize that same concept, but now we're using to find the coefficient. So it works the exact same way. So here in this case, we've got 27.2 grams of barium hydroxide divided by the molar mass of barium hydroxide, and that's where we get the number of moles. Okay, we do the same thing now for water. We're trying to find the number of moles of water, so we take the 22.8 grams that we just calculated, and we divide it by the molar mass of water to get 1.265 moles. So that's that value. So right now, remember what as we said, when we're doing the calculating the empirical, we're always trying to divide one of the coefficients to one. The one that should always be the one that comes out to one is always the number in front of the ionic compound. Why? Because there can't be a number in front of the ionic compound. The only number that should exist is a number in front of water. Okay, so in this case, whatever the ion comment, that's the one that's going to be. If this value happens to be larger than this value, somewhere along the way you went wrong. Okay, so in this case here, the barium hydroxide worked out to 1. The water worked out to 7.96. This 0.96 is very close to 8, so we're able to round it up to 8. So the formula works out to barium hydroxide octahydrate. That's the name of this unknown substance. So the value of that X value in front of water happens to be 8. Okay, so please, I can't stress enough to do the sample problem. Do the sample problems, work them out, do the homework questions, and prepare. We are going to be starting chapter 8 next. In chapter 8, we will have our next, I think, a next assignment. I might test out a quiz in chapter 8, but it'll be a short answer. And it'll just be like, I think, one question. Try to make it nice and simple. But anyhow, chapter 8 is next. It is the last chapter of the unit as well. Okay.
I hope you liked this video. If you did, do not be shy to hit that thumbs up button. And while you're clicking the thumbs up, click on that subscribe to stay tuned to my new videos. Thanks for watching.